is part 4, video D of this section 2.4. This problem is one again of our application problems, one that we're going to be able to see maybe something you can relate to in your business courses. Finding the prices per pound of lean and extra lean ground beef from 1998 to 2005, modeled by this function. Again, I don't know who designed this. I can tell you though that they looked at data, they looked at a scatter plot, and they determined that this function actually would best predict the prices, PSR output, the prices of the lean and extra lean beef with an input of time. Time is between 8 and 15 years. T is the year, with T equaling 8 corresponding to 1998. Now we're asked to find dP dt. Be very careful when you read this. We're looking at the derivative of the output variable P with respect to the input variable T. So we're looking for the derivative of this function. Obviously, we're going to have to use the quotient rule because we do have a quotient for our function there. So find the derivative and then evaluate it for these 4 years and then interpret the meaning of them. So let's start with the first part of it, and that is let's find the derivative of our output variable, our function P, with respect to our input variable T. This is where we are going to definitely need to use our quotient rule. So we're going to start with our denominator, and we will write that as carefully as we can. Make sure we get all those digits in there. Times the derivative with respect to T of our numerator, and this should be a decimal point here, not a comma. Obviously I've run out of space, so I'm going to have to say, continue it down here, minus our numerator, which is, because I've run out of space, let me just do it this way. And I'll just erase all of that, and we'll start again. Let's just say that we have our denominator. I'm just going to do this. This is my denominator. Times the derivative with respect to T of our numerator. Minus our numerator times the derivative with respect to T of our denominator. All of that divided by the square of our denominator. Now, I wouldn't normally do this, but I do want to get all these numbers in. Okay, so, and if you show me this, if by chance I would give you one with numbers, and of course you can write smaller than I can on my board here. We have our numerator, or excuse me, our denominator, and 1 minus and so forth. I'll try to write smaller here. Times my derivative of the denominator, of the numerator. The first term is going to be 0. The second derivative of the second one is just going to be negative 0.2079. Remember, it's going to be t to the 1 minus 1, so we lose the t, plus 3, that's our exponent, times 0.00 673, and that, oh, excuse me, that is a 2, so let's make sure we write that as a 2. So it would be 2 times 0.00673t minus, I'm still going to run out of space, aren't I? I'm just going to put this down here. This is my numerator, and the derivative of my denominator is going to be negative 0.1282 plus 2 times 0.00434t. Even with that, it's hard to get all those digits in. Okay, and so we'll just say the denominator squared. You know, this is one where, do I expect you to multiply all those out? On a problem like this, I would expect you to show me that you understand all this, the quotient rule. Writing all of this out, I understand, can be a real difficulty. So let's just, you can practice on the Inspire if you wish, but let's just go ahead and find out what our final answer is. Okay, what I did when I had this paused was I went back and made sure that I had everything in here correctly, and I also went into the Inspire, and as you can see, I have defined this function. This is one of those that you definitely want to define the function. If you remember, you go into Menu, Actions, and Define, and that then is going to save us from having to write this again. So, and again, I could have written this as P equals, but because I might want to look at it on the graph, I did it as F1 of X. So let's go into Menu and Calculus and pick up a derivative. And because we may want to graph this, we'll continue with the X. Tab, and then all we have to do is say F1 of X. And press Enter. So there is our derivative. Now, if we did it out by hand, we should still get the very same thing. If you did it by hand, you can check your work against this to make sure that it is correct. Now let's go back to this. It says evaluated for t equaling 8, 10, 12, and 14. On a problem like this, I am more interested in your ability to interpret the meaning of these values than I am in your ability to multiply with numbers such as this. So what we're going to focus on now is, given this derivative that we have found over here, if we look at this value at a point, and let's go into Menu. Let's go into Menu and go into Calculus, and we see this, it says derivative at a point. So we're going to have the variable x, and the value, now one of the values that we're looking at is 8, which is corresponding to 1998. And so we'll make 8 here, and we're looking for the first derivative, and our function is going to be f1 of x, and our value is 0.085426. So let's go ahead and write that for us. We'll just put dot, dot, dot. Let's go down here and say dp dt at t equaling 8 has a value of let's check that again, 0.085426. Now, we get an answer, but the most important thing is, what does it mean to us? So if we go back here, the prices P of lean and extra lean beef modeled by this formula where T is year. So what we're saying is that the prices increased approximately and it doesn't tell us a unit here, so we'll talk about in a I would assume it's in a dollar sense here. For each additional year when t equals 8, or in 1998. Which all we can say is that in 1998 the prices of the beef were increasing approximately this much per pound. So we can say per pound on this for each additional year. How does that compare with, let's just jump to 14, okay, which would be 2004. So in our work here, we'll evaluate this at t equaling 14, and let's go back to our Inspire. We'll just jump up and grab that again, change that value to 14, and we see then that the prices per pound were still increasing, but they weren't increasing as fast. And so it's 0.00172, so 0.01732. So in 2014, prices increased approximately 0.01732 per pound for each additional year. It's these explanations that are much more valuable to our understanding than anything else that we can think about. Okay, very quickly before the time runs out, if we talk about this problem, where does it have a horizontal tangent line? If it has a horizontal tangent line, the slope is 0. So we would have to first take the derivative of this function, and it would be x squared plus 1 times the derivative with respect to x of x squared, x to the 4th plus 3, minus x to the 4th plus 3 times the derivative with respect to x of x squared plus 1, all of that divided by x squared plus 1, quantity squared. Again, I don't want to run out of time on this and start a new one, so we'll just get as far as we can, and then we will have to maybe come back on this. Derivative of x to the 4th is 4x cubed plus 0 for the 3. X to the 4th plus 3 times the derivative of x squared is 2x plus 0, and all of it is x squared plus 1, quantity squared. Now we want this to be set equal to 0 to find our horizontal tangent line. When you think about a fraction set equal to 0, can the denominator ever be the 0 factor? And the answer to that is no. So we can only set our numerator equal to 0, and we would have to then solve this. Let's see, this would be 4x to the 5th plus 4x cubed minus 2x to the 5th minus 6x, and 0 is 2x to the 5th plus 4x cubed minus 6x. We can factor out an x, solve it. I leave this for another time so we don't have to start another video. I'll see you next week.